how is the structure of Qualia related to the structure of information? Can we estimate the information structure? So if we can measure and characterize Qualia structure as the previous video was proposing, then this quantification of Qualia structure through relations are possible. And then the next step is the extracting information structure from our brain. And then finally, finding the relationships between the structures of Qualia and the information. That's the sort of the Qualia structure paradigm proposed. So what are the causality or information, causal structure or information structure? So the brain, if you, as you have already learned from this lecture, is a huge network of neurons. And the number of the neurons we have in our human brain is a 10 to the 11. And the number of the people in the earth is roughly 10 to the 10. So it's, really huge number of the neurons inside of our brain, right? And each of the neuron is connected with other neurons through the synapses. And the number of the synapses range from 10 to the 3 to 4 or 5 even. And so roughly speaking, 10 times more people in this, earth. And each of the person knows 1,000 or 10,000 people and then interacting with each other. So that's the kind of situation of our brain at the size of the earth and humans, 10 times more humans. And then the difference between, human earth kind of thing is that each of these neurons are complex, complex manner, exciting or inhibiting and things like that. And each are quite active at a given time point. So why do we need to think about the causality and the information structure? And this is all about anatomical structure and then how this anatomical structure gives rise to dynamical structure, activity states. So why do we need to think about the causality or information structure rather than just a raw structure or raw activity state or MCC per se? The reason is that, as we have been, looking at from IIT's claim, we really can't explain or account for the features of consciousness by doing this, like a conscious versus non-conscious divide. What kind of structure, what kind of activity has to make a decision about, what is conscious and what is non-conscious, unclear. And then phenomenological actions, each of these, intrinsic existence of composition, information, integration, exclusion. How do they actually, explain? We really don't know, and then similarity structures as well. So we need to some kind of, ways to extract and filter out everything that are critical for consciousness and filter out anything that is unnecessary for consciousness. So as a sort of that, primary kind of target or primary candidate of this type of theory, I consider integrated information theory. And but the integrated information theory has been criticized that it's impossible to apply to the real data, but that's not the case. And here's our PhD student Angus Leung. He used the recording from flies to compute the integrated information structure, in fact. So I'll skip all these complicated, mathematical details. And if you are interested in this, you can look at this paper published in PLOS Computation Biology. But here, what we did is to consider each of the neurons or recording electrode side as, component A, B, C, D, and then for each of the possible subsets, let's say, here this is, if this is A and this is B, and then this, connected with these two lines, this AB, how AB constrains A, B, C, D above and beyond A only or B only, and here A, B, C, and so on, and then what does A, B, C, D, constrains the complex A, B, C, D. And by quantifying in small phi or integrated information here, for each of the possible combination of these subset, we were able to capture integrated information structure like this way. And then the central figure shows the amount of the integrated information structure in our awake state fly, and then this is the anesthetized flies. As you can see, the structure actually collapses when the flies are anesthetized. And you might be surprised, but the flies are indeed anesthetized and then do not move under the anesthesia. It's very, the same drugs that works for human does work for the flies. And this kind of knowledge that, many of the animals seem to behave in a similar way like us is one of the, the requirement for us to understand what the other people or other animals would be experiencing, as I argued at the end. Anyway, so something similar can be done even from the human experiment, which we haven't done properly, but this is sort of sketch of what we can do. This is a part of the study that we published in 2017. Here, we present some stimulus like face, and then that is masked by the continuous flash suppression. And then sometimes it is perceived as face, sometimes it's not. And standard MCC kind of paradigm. But then what was different here is that we were able to record the activity from the epilepsy patient. And in particular, we had some kind of situation where the electrodes was included to sample from the FFA, face areas. And then this is the recording trace for the all these 4 electrodes, A, B, C, D. And then each of them selectively respond to the face or non-face and things like that. And from this, we can again construct the integrated information by looking at how much AB constrains everything, or BC and ABC and ABCD. And then by visualizing this type of the structure, integrated information structure, we get something like the following. And here, the interesting outcome was that first of all, under the continuous flash suppression experiment, when the face was invisible, then it generated completely different types of a shape compared to the invisible CFS condition. I'll just replay. Okay, invisible case doesn't generate the same kind of structure. Okay, and then in a completely different setting and different experimental setting of the backward masking, where we use a different type of face. Okay, and the task instruction was also completely different, finding the face in one of the 4 locations rather than reporting face was seen or not. But as long as far as the patient's experience wise, the same kind of face experience was observed on the left side and backward masking and also CFS, and the structure of integrated information was similar, highly similar between these 2 types of the experience of faces in 2 different experimental paradigms. So that means that it is highly promising to think about this causality structure is related or potentially explain the feature of conscious experience of face from here, this recorded from this region. So in summary, information structure can be estimated from already available neural recordings. However, this is a big however, we still don't have the most critical data set. And without these, actually, our estimation of this integrated information remains very coarse and most likely incorrect estimation. We need a precise understanding of the structure of the connection and so on from neural data. And also we need to monitor activity of all the neurons ideally. And then we need to manipulate these activity states of structure. And then at the same time, we want to get the information about the qualia that our subject has. So in the case of fly, we don't have that qualia report. In the case of the humans, we don't have the structure and the activity. So getting all of them at the same time is going to be difficult. But as you have been seeing on over the last a couple of lectures, converging evidence from many different kind of systems and many different paradigms can get there. And then if the IIT is wrong, then at any stage, many of the evidence that comes from one approximation or another will be eventually become very stressful to fit with the theory. So that at that point, IIT will be discarded or have to be significantly revised. Meanwhile, other theories at least need to try to explain the feature of consciousness or Qualia structure to the best they can do. Okay, so then, but once we know what we need, scientists also have been always figure the way that, to get there. So for example, I have probably shown this figure before, but the number of the electrodes that people can insert into the animal and then record neurons increased really significantly. In 1950s, one electrode at the time is the maximum what they can do. And then when the silicon probes were invented, the number of the simultaneous recording increased really significantly logarithmically, and now it's routinely around 100. But around 2010, this new technology called the neuropixel started to become available, and then now people are routinely including the inserting this many of them in the same animal. And then eventually, one of the papers that were published recently already reports like this kind of sampling for the rat brain or mice brain. And so we can expect many neuron recording in a foreseeable future. Okay.